I'm Eric Larsen. I'm with the Immersive Technologies team at AMD, and I'm going to talk to you about our development of a plugin for FEM physics. So basically, I'm going to start by giving a bit of background about FEM, the method, the R&D we've done, and the implementation of it. And then move on to details about the UE4 plugin, how we were able to use the plugin to accomplish some of our goals, some custom rendering of the FEM objects that we're simulating, and custom U assets, and creating scenes, and then show you demos that kind of show you basically what we did with the system and the combination. To talk about the method a little bit, it's a physics method for simulating deformation, and it represents solids as a volumetric mesh of elements, which can be different elements, but often tetrahedra, like at the right, in the four vertex shape, very simple shape. Each element has parameters that describe or define the way it behaves. And basically just sort of summarizing what each of these sort of means intuitively. There's control over stiffness of the material, control over how volume changes when the material is compressed, and a couple of stress limits which decide when the material can break and also take on permanent deformation, plastic deformation. So it has a range of applications because there are a lot of different types of deformable materials. And so, we give some examples there of materials that we've put into various scenarios. So it can do deformation of metal and wood materials, for instance. It has a ability to do a melting kind of effect based on the plastic deformation. So you can change the material to cause things to sag and melt. And then there are some unusual, what I call alien materials that are kind of tissue-like, like what our tech artist, Chris Woods, has been playing with, and we have some examples of that. So one of the goals of it is greater fidelity in physics simulation in general. There are a lot of deformation-related effects that occur in the real world. And that includes things flexing and oscillating, the way that objects can absorb energy, elastic energy, and then release it. You can see effects from that, how they spring back, or actually how they snap when they break. And even some stiffer materials have enough deformation that it can affect the look of the material. And so that's kind of one of the goals is getting maybe a more realistic look and less brittle look for materials like wood. We're interested in different types of interaction we can do with objects that are deformable, and inspired by a number of examples that have been created previously, such as by DMM middleware and MPC's Kali systems that use FEM for effects in games and for VFX. So I'm going to start with a demo here. Shows you metal deformation on this car. We've got rubber ducts, but we can also turn on the heat. Liquefy them. And here's some wood panels that show us a bit of that flex and oscillation. So go ahead and show a couple of other examples. These are a little cruder looking, but they show a few different materials and interactions. And And these tires have a nice bit of bounce. And one last one. This is showing just the melting effect applied to the car body. Okay, so I'm going to talk a little bit about the implementation details of the FEM system we made. So it's really a combination of methods from a lot of different sources, published methods that we've altered or custom solutions we found. And it's a multi-threaded CPU implementation. It is basically taking advantage of the recent trend in additional cores and CPUs, including AMD cores, CPUs, Ryzen. And we included many SIMD optimizations as well in the implementation. I'll go over a few of the highlights of different methods and features that the library has. First of all, implicit integration is very helpful for stiffer materials. So it gives you the power to kind of go from soft, completely soft objects to things closer in the spectrum, to rigid, like wood and metal, for instance, are behaving very stiffly. And then it also basically enables proper behavior for those types of materials. It also has constraint-based contact, and the advantage of that, this is similar to the type of numerical method that is used for rigid bodies. And for rigid body solvers, the benefit is stacking and good resting contact behavior. So it has that, and then also that provides potential path for integrating, interfacing basically with rigid bodies. And it has continuous collision detection, which is a method that can help with collisions with very fast-moving objects, so they don't just pass through something before collision is detected. And but it's used in general. It can improve collision quality, basically, and kind of simulation quality in general. And we're using a kind of an iterative method that's based on like geometric tests, distance tests, as opposed to some which I've seen are more algebraic, like solving an equation. And as well, we have multiplicative plasticity, which is a particular type of plastic deformation, or a model for plastic deformation. We ended up using that one because we found that the additive model had certain issues, particularly for objects like the car that are plastically deforming, but not, anchored to the ground, basically. And in general, the momentum behaved better for these objects with that type of plasticity. And also, it has some parameters that control how much plastic deformation you can have. And those are fairly intuitive, basically. It kind of gives a sense of how much something can be squashed or stretched out, basically. And so that's kind of a nice feature. The library also has the ability to put objects to sleep when they are resting. And that, of course, is helpful for performance. Things will wake up when they are collided with again. And we also have a particular feature for fracture, which calling non-fracture groups. Those are groups of tetrahedra in the model that you want to group together and have no fracture. And it's just worth pulling out because they're kind of like changes to the way that the fracture method operates to enable that sort of situation, to have it be able to carefully only break where it's allowed, where it's legal. So want to stress that the message isn't that FEM is good for every situation, or that it's intended to really like replace rigid bodies as a tool for all the great things that they do. And in fact, what we're kind of really more interested in the future is having a good interface that allows you to mix the different representations and different effects. So we've done a little prototyping with this. We do have proof of concept, basically, which is kind of like a definition of an interface that helps the two systems to talk together. The solving method, as I mentioned, is similar to rigid bodies for contact. And so given the way that that works, you can actually have two different systems work on the same problem, but you have to kind of fuse them together at some level, which is usually a deep level in the systems. So so we've done that with a sort of example rigid body system, but in the future, we'd like to look at integrating with a full rigid body solution. And just some future work, potential R&D is switching between FEM and rigid body representations for the objects that we're simulating now. So we've done a lot of work on multi-threading, and that includes seeking out all the parallelism we can find. We've done a lot of the easy parallelism so far, I guess, and some harder parallelism. So easier in a sense is across objects. Different objects are independent, and they have, or at least in many parts of the system, they're independent. And then also you have collision pairs, which can largely be processed independently. And for the constraint solver, there are basically there's independence between groups of objects that are in contact or have constraints, and each one of those, which is usually called an island, is independent and can be simulated at the same time as another island. But within one island, it is a trickier problem to parallelize because of the fact that you have many constraints which touch the same parts of objects and the same state values. And so that creates basically race condition, and any of these updates that are done with this algorithm need to be synchronized or serialized, that is. So we have an approach to solve that, which we're still refining, but it offers speed ups for the single pile case, and it involves basically partitioning the problem and then analyzing different partitions and pairs of partitions to find independent work. And then additionally, there's some scheduling of the independent work in sort of different independent sets in order to improve the utilization and improve the scheduling basically of these workloads. Okay, so I'll talk a little bit about the threading approach in general in the library. We've moved over to what some people call like the async threading model, instead of having your dispatches of parallel work basically submitted and then you wait on a thread for the completion of all of them. Instead, you have all of your dispatch tasks detect when the work is complete, and then one of those tasks will actually send or dispatch a new task to continue the execution. So there's a potential performance implication of the case where you're waiting, because the thread that's waiting, could be actually put to work on another task and be held up in terms of continuing execution. But what we found is the main benefit that we've discovered with it is that it basically puts all the onus of synchronization into the library side that we made, and so there is less for an outside system to have to worry about in terms of scheduling tasks. There isn't any synchronization that the system has to do. We also, part of this was bringing high-level threading features into the library, things like parallel for and task graphs, which are sometimes part of external threading systems. We developed within the library, and part of that was for customization because for our task graph had some particular requirements for how we were doing the solver and the solver optimizations. But down at the the interface level with an outside application or engine, what we have is basically callback interface to let you actually have the scheduler swap in whatever scheduler you want for that. But it's pretty simple in terms of what it is asking for, just an async task call. Okay, so to render these FEM objects, I'll just explain the method that we used. Like a number of publications, we have two meshes. We've got the simulation mesh and we've got a render mesh. And the benefit of having that is that the render mesh can basically have whatever detail you want to include, a lot of fine detail potentially that you don't have to have in the simulation mesh. And the simulation mesh then acts as a control mesh for deforming the render mesh. And to make that work, you have to find correspondence between the vertices of the render mesh and the simulation mesh tetrahedra. So each render vertex is assigned to some tetrahedra, and it gets weights. And then the weights are used sort of like skinning. It can be done, in a vertex shader, basically. So to handle the fracture scenario, we actually pre-author the render meshes for all the potential pieces that could be created. And then, when fractures occur in the simulation mesh, we have to make some updates to the rendering so that, specifically so that parts of the render mesh, I guess I should explain that when you initially assign the correspondence between the render mesh and the sim mesh, you may pick one tetrahedron of the sim mesh to assign it to for the best sort of deformation effect. And after fracture occurs, the important thing is that you keep the render vertices together with other render vertices in the same piece. Because, obviously, if it spans between one piece of the simulation mesh and another, then as they separate, you just get stretched out polygons. So, which, I've witnessed as we tried to root out bugs and things like that. So, I mean, that's a something we finally figured out. But so I'll show you a little bit about the buffers involved for this, and a little detail about how this works. So what we have is a buffer for vertices, and the vertices have references to the tets and the weights that they're assigned to. But actually they're pointing to, in the fracture case, they're pointing to a group of tet assignments, which are all the ones that render vertex could potentially be assigned to after fracture happens. And then we have a buffer of offsets, and those offsets basically are for selecting which tet to assign a render vertex to. And one of the points of doing it this way is that a lot of the render vertices have the same offset. They can use the same offset because they're basically all affected by the same fractures in the simulation mesh. So it helps to kind of condense the amount of data that you have to actually change as fractures happen. The only offsets have to be changed, and only one offset for potentially many render vertices. So how we approached doing this kind of rendering with an Unreal plugin incidentally in version 4.18. First, I want to say UE4 turned out to be very flexible for what we were trying to do, and we found it useful for prototyping. We iterated on the approach and the buffers that we used a few times within UE4. And the basic parts for implementing this were deriving a custom mesh component, which has all the geometry for the FEM object, and an associated scene proxy, which has copies of buffers that are used in the rendering thread. And then we have a derived vertex factory. And the vertex factory is basically representing our vertex shader with the deformation. And it has associated shader parameters, which will point to resources, basically. And let's see. The examples that I showed there, procedural mesh component and the local vertex factory, are implementations of these classes, mesh component and vertex factory, that were in the engine. And they were very helpful because they provided an example that was close enough to what we were trying to do that we could basically just start with them and make modifications and get the behavior we were looking for. So, we took these things and added all of the custom stuff that we needed, additional attributes in the vertex factory for the vertices, and custom resource parameters and custom resources as well for all the different types of buffers that we need. For the vertex shader, we used the structure of the local vertex factory shader, but added the vertex deformation in there, so it does the weighted sum of simulation mesh vertices instead of just a simple transform of the position. Okay, so just to give a little bit of detail about the scene proxy. The scene proxy contains the buffers that have to be updated on the render thread. And we have dynamic updates to them because the simulation meshes are deforming, and because of fractures, we have to change these offsets that I talked about. So we used structured buffers for this, and just giving the usage flags just to show you what we did, essentially. Using the dynamic usage flag seemed to be appropriate as the CPU write, GPU read situation. And then as well, if you're not familiar with this, the buffers have to be updated on the render thread. So the lock and copy of data and unlock would have to be on the render thread. And that involves enqueuing the updates. And there's an enqueue macro that lets you do that. Okay, so the rendering part is covered, but that was only one piece of the overall plugin design and architecture. And so basically I'm going to cover that now. And that was developed by Ryan Main. And the philosophy was, in general, trying to make the plugin be as much sort of best practices or sort of UE4, the UE4 way as possible, basically. So we tried to find relevant examples from the engine and also focus on blueprint interfaces, tried to give as much artist control or designer control, so no C++ interfaces, and also anything that's tunable we wanted to have available in the editor as well. So we also developed this alongside of the library and the demo. So the demo gave us plugin requirements, and the plugin gave us library requirements, and it was, doing that in tandem, I think, was probably a good process. So the basic plugin usage is importing data from a special file, a .fem file, then creating a component, and then creating a scene for the object to be placed in, and attaching a component to an actor. So a little bit more about the FEM format that we created. It's a text format using JSON and syntax. And then it is output by special tools that we created in a Houdini. And it contains all of the information in one file for what we're doing in the plugin. It has the simulation mesh information, it has the render mesh information, and any pre-processing that the authoring tool does. And it includes some tags, which I'll talk a bit more about in a minute, and rigid bodies, which we're not using all that much at the moment, and constraints that can be authored. So we have some examples like glue constraints. You can pin two things together. And that sort of thing, those constraints are used like in the car, for example, attaching wheels and the hood. So yeah, everything has to be imported into Unreal using a factory. So talk about that a little bit. We basically were, should point out that it was a really important decision, and the right decision, to try to make actual custom U assets in Unreal, because previously we had data in file formats that were read at runtime, and you had to keep them basically alongside of Unreal data. But in developing U assets had a bunch of advantages. We could serialize them and then package them with our demo, and also that was the key to making the objects visible in the editor before you actually play the simulation, which is kind of handy when you're trying to actually construct a scene. So in the two U assets, custom U assets, were the FEM mesh itself, which is basically containing all the information from the FEM.FEM file, and then TEP-mesh parameters, which are a U asset for the simulation parameters, the material parameters. And so yeah, each of these needed a factory. The point here is just that the FEM mesh factory is using one of the overrides, the factory create file, in order to do the .fem loading and parsing. And then the other factory for TEP-mesh parameters is just one that uses the factory create new. So about the tags, those were a feature that are part of the .fem file and can be authored with the tools we have. And this is a way of just applying a name to a group of TETs in the model, and that define things that you might want to apply some property to, particular material parameters, or if you want to make them immovable, or other things potentially. Basically, once you combine them with other blueprint interfaces, there's a lot of power to use the tags in new ways. So that turned out to be very handy. And then as well, for blueprint development, creating custom events for collisions and for fracture also helped with being able to add specific gameplay events, and also audio or special effects, particles, things like that. The collision and fracture events have information that's exposed by the library, basically, where in the meshes these things happened and positions that can be used. So here's a couple of just quick examples of blueprint interface uses that involve the tags and the events. So to give you a bit of a fuller picture, I'll do a couple slides on the content development and the tools in Houdini. And basically, Houdini has a lot of helpful utilities for some of the tools we were creating, including creating the tetrahedral meshes that we need for simulation. And we can do that by inputting a surface mesh and using certain nodes that will generate the tetrahedral data. And also custom things that we did involving pre-processing those render meshes and attaching them to the simulation meshes. And I mentioned the tags before, but actually in the authoring tools, you can select a group of tets and do a lot of different things to affect behavior. Apply particular materials to that grouping. You can mark them as that non-fracturing group I was talking about before, or mark them as fixed. Kinematic. Actually, as kinematic, they can be fixed or moved, but programmatically moved. So the idea behind investing time in this tool was to have, again, something that's artist-friendly, lets you actually iterate rapidly and create some more complex and interesting examples. And that's certainly I agree, because the original tools were all command line tools and not for which were fine when I was playing around with a couple of test models, but not good for more interesting, cool looking things. So about the Houdini integration or the implementation of that, just to clarify, this was several surface operator level nodes, and the only inputs required are the simulation surface mesh and the render mesh or meshes. And it exports to .fem and provides all the data that we use. So I'm going to show another example here, several examples created by Chris Woods, with assets created in Houdini. This one shows some interaction between different materials. It's got these cool alien vines. He's come up with some gameplay examples using that. Okay, so to summarize, I showed some details about FEM and explained a lot about the work that we've done with it, the R&D and the implementation. And then I've shown how we were able to achieve our goals for creating content using that simulation system with a custom plugin, and customize our rendering and also generate a lot of content rapidly. So, thank you.